planets are almost as common as stars in the galaxy. Of the many hundreds of billions of stars in the Milky Way, a significant portion of them have gravitationally bound systems of planets orbiting them. And while many are radically different to ours, they all share some key characteristics which can give us clues about how they came to be formed. Knowing the life cycles of stars and their planetary systems provides us with crucial insight into the mechanisms that gave rise to them. And it is with this insight that we are finally beginning to understand the events that unfolded at the birth of the solar system. Before we dive into all that, we first need to know about the solar system, because the arrangement of a planetary system can give us clues about its origins. Today, the solar system is about 4.5 billion years old, and is home to 8 known planets. 4 smaller rocky terrestrial planets on the inside, and 4 large gas and ice giant planets further out. 6 out of these 8 planets are home to at least 1 moon, but the largest have dozens. Some so large and complex that they would be worlds in their own right were it not for their captivity around their giant host. In addition to the planets and moons of the solar system, there are dozens of small dwarf planets, millions of rocky asteroids, and trillions of icy chunks arranged into bands and belts around the Sun. The outer part of the solar system consists of 3 regions: the Kuiper Belt, the scattered disk, and significantly farther away, the hypothetical Oort cloud. 3 collections of volatile ice chunks which formed closer to the Sun before being scattered by gravitational disturbances. The Kuiper Belt begins just beyond the orbit of Neptune, and it extends to around 55 astronomical units. An astronomical unit is the distance at which Earth orbits the Sun, just under 150 million kilometres. In comparison, the scattered disk extends much further, to over 100 astronomical units away, and the hypothetical Oort cloud is thought to start at around 600 astronomical units, extending for over a light year into interstellar space. In reality, the full scale of the solar system is so enormous that even light, the fastest thing in the universe, takes more than 18 months to escape the outer edge. However, the vast majority of the system's interesting features, including the most peculiar feature, life, are concentrated inside an area within about 50 astronomical units of the Sun, an area protected from harmful interstellar and intergalactic radiation by the Sun's heliosphere. The solar system today lies in a peaceful balance, with each of its 8 planets bound in predictable near-circular orbits. The small rocky planets sit neatly on the inside, with the larger gas giants further out. And so for a long time, we thought that this was the natural arrangement of most planetary systems. However, since 1995, we have been able to peer into the planetary neighbourhoods of other stars, and what we've realised is that systems of planets are very rarely this well structured and settled. Planets of all sizes and types can be scattered throughout their respected systems, and they don't necessarily stay in circular orbits. In fact, it is a fundamental property of planetary systems to be dynamic, which can profoundly alter the system's destiny. And it appears that we are no exception to this. Despite the neat arrangements of the planets today, it's likely that the solar system once looked like a very different place. Sadly, we as humans woke up far too late to witness the dynamic young solar system firsthand, but we are able to see the effects of certain key events that occurred early in its life, which allows us to start to put together a timeline. And thanks to telescopes like Hubble and Kepler, we've surveyed, catalogued and deduced the characteristics of thousands of other star systems at every stage of their life cycle, from their gaseous births to their violent deaths. This observed life cycle has helped us to connect the dots on a number of key questions regarding the formation of the solar system. The culmination of these decades of research is presented in the Nebular Hypothesis, our model for describing and explaining the birth of the solar system and all other star systems, and it is generally agreed upon by most scientists. It's not without its unanswered questions and areas of ambiguity, but for the stuff that we do know, we have large amounts of observational data to back it up. The Nebular Hypothesis tells us that star formation begins inside massive, cold clouds of gas in space, containing many different elements and compounds, mostly hydrogen and helium, but often with a small portion of more complex stuff. Organic molecules, hydrocarbons, silicates, and various forms of volatile substances like water and methane. Because these clouds are so enormous, stars rarely form in isolation. Around 90% of stars, including the Sun, were most likely born within a stellar birth cluster, which formed together and then later dispersed. The thing that makes these clouds so good at producing stars is the fact that they are gravitationally unstable, highly asymmetric with an unevenly distributed mass, meaning the cloud is always moving and interacting within itself. As such, these clouds are prone to internal fragmentation. Internal areas of the nebula with a higher particle density detach from the overall structure of the cloud and begin contracting due to gravity, acting as a smaller, denser nebula. Within these denser fragments, pockets of gas ranging in sizes from 2,000 astronomical units to 20,000 astronomical units start to form. It is within these pockets, also known as protostellar nebulae, that star systems like the solar system form. The birth of such a system always begins with angular momentum. While all the necessary ingredients for stars are present within protostellar nebulae, something needs to wake the cloud so that it can collapse and form a star, essentially giving the nebulous mixture a gravitational stir to set the processes into motion. Once something has acted upon a pocket of gas like this, it begins to rotate, pulling its contents into a vortex. The speed at which the nebula rotates flings the gas within the protostellar nebula out on its orbital plane over thousands of years, resulting in a fast-swelling accretion disk forming from the matter, which feeds gas into the centre. Gas orbiting in this disk accelerates the closer it gets to the core, compressing matter around the centre and concentrating mass. This process continues for about 100,000 years, until a central, stable sphere of hot gas, which is no longer contracting, forms at the heart of the disk, the seed from which the star will arise. As gas continues to be fed onto the seed, a dense envelope of infalling matter collects around the seed, acting as a gaseous oven for the star by raising the mass, compression, density, and ultimately the temperature. Eventually, the mass and pressure is sufficient enough that a protostar ignites within, the first stage of a star's great furnace. At this point, the star is not hot or massive enough to begin nuclear fusion, the process powering main sequence stars like the Sun. Rather, at this point, the only energy and heat source comes from the gravitational compression of the envelope, which compresses hot swirling gas around the star, increasing its mass and density, often accompanied by characteristic twin polar jets of outflow gas. Before long, a substantial amount of the protostellar nebula's matter is concentrated onto the protostar. What remains of the accretion disk feeding the envelope will not exceed more than about 1/5 of the star's total mass, and as material is used up within the system, the envelope around the star begins to deplete, and the infant star becomes observable for the first time, first in the far infrared spectrum, and then later in the visible spectrum. It has become a young stellar object. Around this time, providing that the star is at least 13 times heavier than Jupiter, it reaches the stage at which it can begin nuclear fusion. Regardless of its total mass, it cannot fuse hydrogen yet, but instead fuses deuterium, which generates much less outward pressure. If the mass accumulated by the protostar during incubation does not exceed around 80 times the mass of Jupiter, then the star will not evolve beyond this deuterium burning stage, and will remain floating through space as a small dim brown dwarf star, a failed star whose light fades away over billions of years. However, for the stars that are above this mass limit, they will be able to fuse hydrogen eventually, and will start evolving into their main sequence burning phase, slowly, over tens of millions of years. In the meantime, the young star is at last generating some kind of outward pressure, and begins erupting jets from its photosphere, which blows away the last of the gaseous envelope. This envelope takes about 1 million years to become transparent and clear completely. The young star is now fully visible, and is classed as a T Tauri star. T Tauri stars are named after the first of their kind that was discovered. They are young stars which generate a broad range of emissions, owing to what remains of the accretion disk that has not yet had time to form into planets. This material hits the now fully exposed star's surface on the poles, creating a variety of spectral emissions, magnetic activity, and often twin polar jets which we can detect from the Earth. The classical T Tauri stage lasts around 10 million years, by the end of which time the accretion disk has cleared completely. Therefore, during this stage, a brief window opens for planetary formation. The accretion disk becomes a protoplanetary disk. This is the make or break stage for the star's system. While planets can take billions of years to change and evolve, every planet within a star system has to form within this brief 10 million year window, or else it will never form at all. At the very start of the T Tauri stage, the disk is far too hot for anything to form. The temperature within 4 astronomical units of the star will be around 400 Kelvin, and the temperature within the distance from Earth to the Sun is around 1000 Kelvin. At this temperature, volatiles like water and methane are easily vaporized and ejected towards the outer regions of the disk. But as the T Tauri stage progresses, material clears and the disk cools, and less volatile substances like silicate rock and iron begin condensing, forming tiny crystalline dust grains. In a dense rotating disk environment, dust grains are drawn to one another by various natural processes, the main one being gravity, which causes them to clot and form clumps of dust grains up to 1 centimetre or 2 wide. These clumps then float through space, attracting and sticking to other clumps, growing at a rate of a few centimetres per year. After 1 million years or so of this process, large chunks up to 1 kilometre wide have formed, known as planetesimals. Once the planetesimals have formed, they too begin attracting and accreting material from the disk. This process favours larger bodies, and within 100,000 years, runaway accretion processes have given rise to rocky bodies more than 1,000 kilometres in diameter. These bodies then dominate their region of the disk, sweeping up much of the leftover material at the expense of smaller bodies. By the time the planetary formation window closes after 10 million years, the majority of the system's mass is concentrated within a few dozen large rocky bodies, known as planetary embryos. Once the disk has dissipated and accretion is no longer practical, collisions take over. Planetary embryos smash into one another in chaotic encounters, generating enormous amounts of heat and friction, before eventually sticking together. Once these rocky bodies reach a certain size, they become so massive that their heavier elements and metals begin sinking towards the heated core, and the planetary embryo slowly becomes a differentiated planet with a hot, internal layered structure. This is how rocky terrestrial planets like Earth, Venus, Mars, and Mercury form. And as mentioned, they tend to be found closer to their parent star, where the disk used to be much hotter, an area where only silicate rock and metals can condense to form planetesimals. However, silicates only account for a negligible portion of the protostellar nebula's mass, and so there simply isn't that much silicate rock to allow terrestrial planets to grow exceptionally large. The majority of the protostellar nebula's contents is hydrogen and helium gas, and this remains within the disk as planets begin to form. And further away from the young star's heat and radiation, space becomes cold enough for the volatiles that were ejected from the hot part of the disk to condense into a solid form, known as ices. And volatile ices provide an abundance of extra material for planetary formation further away from the star. More remote planetary embryos which can attract these ices can quickly grow to dozens of times the mass of rocky terrestrial planets, heavy enough to begin attracting hydrogen and helium from the surrounding disk before it is driven away by the young star. These attracted atoms form a thick atmosphere around the icy planetary core, eventually becoming so large and heavy that the whole thing becomes this indistinguishable dense ball of extremely compressed liquefied gases, also known as a gas giant. On the other hand, ice giants, such as Uranus and Neptune, are thought to be failed gas giants which formed later on in the system's planetary formation window, and subsequently were able to accumulate much less hydrogen and helium. However, they still retain thick coverings of volatiles and can be dozens of times the mass of the Earth. Be it gas or ice giant, these massive planets often barrel around their respected star systems after they form, crossing orbital lines and providing gravitational kicks which sends other planets' orbits into chaos. Planetesimal material that has not been used in planetary formation thus far is scattered by these influences, often collecting into large circumstellar belts of rock and ice further away from the parent star, like the Kuiper belt for example. Eventually, the protoplanetary disk is either accreted by planets, vaporized by ultraviolet radiation, or scattered out of the system by the star's emissions. One way or another, no more than 10 million years after the T-Tauri stage begins, the planetary formation window closes for good. What remains is either a fully formed system of planets, or a lone star with a failed dusty disk. For us, of course, a vast and beautiful planetary system was left behind. A system that gave rise to life so complex that it is capable of comprehending these incredible events that occurred billions of years ago. So that's the science of a star system, but what about the story? What is it that makes this place unique from the rest? What happened when our solar system was born? As the Nebular Hypothesis tells us, the solar system began with a giant interstellar molecular cloud, around 65 light-years in diameter, within which smaller pockets of gas were fragmenting and acting as isolated protostellar nebulae. One such pocket, known as the Solar Nebula, or pre-solar nebula at this point, was where the solar system would begin its journey. As we know, star formation begins with angular momentum. Something must have provided the kick into life to initiate the formation of the Sun. We believe that this thing was the supernova of a nearby dying star, which generated a huge shockwave that cascaded through space. This shockwave struck the molecular cloud and pre-solar nebula, causing them both to rotate and showering it with heavier elements released from the dead star's core. This shockwave reverberated throughout the entire cloud, awakening hundreds of individual protostellar nebulae. A whole host of new stars, including the Sun, were forming inside what is known as the solar birth cluster. In spite of the fact that we are far away from our stellar neighbours today, current simulations of the solar system suggest it began within a group containing 200 to 400 stars that formed from material in the same molecular cloud. These stars formed in close proximity, but were not as close, dense or populous as, say, a globular cluster, and so it wouldn't have taken much for these stars to escape one another's gravity. Stars within these kinds of clusters are born with momentum, which carries them away from their original position while the system within takes shape. Eventually, constituent stars in the cluster are carried far enough away that they begin to independently latch onto and orbit the galactic core of the Milky Way, which continues to carry them around the galaxy along their own path until the cluster is completely dispersed. It took hundreds of millions of years for the solar system to migrate out of its birth cluster, long after the planets had taken shape. Around 100,000 years after the solar nebula began to collapse, the Sun had begun forming inside its gaseous envelope, and eventually, the surrounding gas in the nebula was flattened into a protoplanetary disk around 200 astronomical units in diameter. Within a million years, its contents had crystallized to form dust grains, which quickly clumped together, forming both rocky and icy planetesimals soon after, thus ushering in the planetesimal era of the solar system, and opening the brief window for planetary formation. And only a few million years after this window opened, the solar system knew its first world. As we briefly touched on earlier, in every star system there is a boundary, a certain distance from the parent star, the area beyond which it is cold enough to allow volatile ices to condense into a solid form. The solar system is no exception, and its snow line lies around 5 astronomical units from the Sun. It is no surprise that the oldest and largest planet of them all lies just around this boundary. When the young Sun was forming, vaporized volatiles ejected from the inner solar system began condensing around the snow line. This led to the rapid accumulation of water vapor within the vicinity, which created a circumstellar region of low pressure. This meant that particles in this area could orbit faster, preventing them from falling further in towards the Sun, effectively creating an orbital barrier which enabled a faster buildup of dust. This band of dust then coalesced into a planetary core about 10 times the mass of the Earth today, massive enough to start attracting the early hydrogen and helium atoms from the surrounding disk. Within about 100,000 years of the planetary core forming, it now weighed more than 150 times the mass of the Earth, and for the first time, the Sun rose on the horizon of its firstborn planet, Jupiter. Jupiter formed around 3 million years after the solar system, and in addition to being the first planet to see the young T-Tauri sun rise, it also had access to the untapped supply of dust in the protoplanetary disk. As Jupiter began to accrete abundances of material after formation, this in turn dragged the planet slightly inwards, causing it to veer off its orbital path and spiral towards the Sun. It barreled through the young solar system, clearing vast trails in the protoplanetary dust, allowing it to become far larger and heavier than all of the other planets of the solar system. And today it is around 320 times the mass of the Earth, 2.5 times heavier than all of the other planets combined. Shortly after Jupiter formed, another gas giant was coalescing from the dust around the snow line, Saturn. But not with the brilliant ring system that we know it to have today. While Saturn is a similar size to Jupiter, it is considerably lighter, most likely because Jupiter had already consumed most of the material that could have been used to grow Saturn. The same can be said for the solar system's ice giant planets, Uranus and Neptune. They both formed shortly after their gas giant siblings, and by this point the young sun's emissions had scattered most of the hydrogen and helium gas that was left in the disk. And so it is not surprising that the ice giants are much smaller than the gas giants, given when they are thought to have formed. The real mystery is where. In their current remote positions, there wouldn't have been enough time during the planetary formation window to allow the ice giants to form and accrete to such sizes. There simply wasn't enough dust that far away. What this suggests is that the two ice giants formed further inside the solar system, around or perhaps even between the orbits of Saturn and Jupiter, and it wasn't until much later that they migrated outwards. Meanwhile, in the inner solar system, once the planetary formation epoch had ended, we estimate that there would have been between 50 to 100 Moon to Mars-sized planetary embryos, which then began colliding to merge and grow in a chaotic process of planetary natural selection. It's likely that a number of would-be planets from this age have since been lost due to various violent events. Mercury is one such example. It is very small compared to the other terrestrials, and its internal structure constitutes mostly a planetary core, suggesting it was once a budding protoplanet in the making before another planetary embryo struck it. This collision likely tore off its outer mantle and sent the exposed planetary core hurtling in towards the Sun, where it has settled, healed, and remains to this day. Mercury is an example of a failed world. But slightly further away from the Sun, the fortunes of three other terrestrial planets were much different. Venus, the Earth, and Mars all formed from collisions of planetary embryos, which heated their cores and allowed them to grow to the point at which they gained internal layered structures, allowing for magnetic fields and geological activity, which protected their early atmospheres. After the planetary formation window closed, it took around 50 million years for the Sun to fully evolve into a hydrogen-fusing main-sequence yellow dwarf, and another 50 million years for the terrestrial planets to form completely as we know them today, thus completing the solar system's present-day structure. After this, planetary migration took over the fate of the solar system for the next billion years or so, and the gravitational influences of the giant planets sculpted the solar system into the arrangement we see today. Between 500 or 600 million years after they formed, Jupiter and Saturn fell into a 2-to-1 orbital resonance, with Jupiter completing 2 orbits for every 1 orbit of Saturn. The combined co-moving tidal influences of the two giants acted as a gravitational slingshot, and it is thought that this influence is what kicked Neptune and Uranus out from the snowline region towards the positions that we see today. When this happened, the young Neptune ploughed into what was the Kuiper belt back then, which was much closer to the Sun, starting at 15 astronomical units and extending to only 20 astronomical units. But Neptune's influence coursing into this region disrupted the belt and scattered its objects in all directions. Some of the debris was sent hurtling into the outer solar system, where it collected into what is now the present-day, more remote Kuiper belt, and the larger scattered disk. But other planetesimals were less fortunate. They were sent inwards towards the Sun by Neptune, where they then encountered the gravitational influence of Saturn and Jupiter's resonance. This ejected the planetesimals back out of the solar system with much more force than Neptune could muster, sending them far into interstellar space, into what is now believed to be the Oort cloud. Further in, and the cascading influence of Neptune's departure to the outer solar system was wreaking havoc on the asteroid belt, the sparse circumstellar band of rocky asteroids that lies between 2 to 4 astronomical units from the Sun. Today, its mass is barely a fraction of a percent of Earth's, but back in the early solar system, it was much more densely populated, with enough material to form another 2 to 3 Earth-sized planets. This material was in the process of collecting into planetary embryos before Neptune and Jupiter's influences sent the belt into disarray. Each of the terrestrials was pounded by asteroids for around 300 million years, in an event known as the Late Heavy Bombardment, causing chaos to rain down on each of the planets. But among these many asteroids, something else was arriving: water. As the unrelenting chaos of the early solar system ensued, icy planetesimals scattered by the gas giants from further out came hurtling into the inner solar system as comets, many of which also smashed into the terrestrial planets. The water contained within these comets instantly vaporized on impact, but this vapor was retained within each planet's early atmosphere. Gradually, each of the terrestrial planets cooled down from their primordial states, and as more and more water arrived, the balance of each world's atmosphere changed, allowing the vapor to condense in the sky and fall as rain. For thousands of years it rained on each of the terrestrial planets, filling streams, basins, and eventually entire oceans with liquid water. Nowadays we know of Earth as the blue planet. But in the early solar system, it's more than likely that there are actually 3 blue planets. Not necessarily occurring at the same time, but we believe that both Mars and Venus also once harboured oceans of liquid water like on Earth today. Water certainly once flowed on Mars's surface. We can see evidence of smoothing, weathering and erosion all over the face of the planet. And many of our efforts to Venus since the 1980s suggest that it may have had shallow surface coverings of liquid water for around 2 billion years. All 3 planets were once home to similar temperate ocean environments, likely made habitable by the same complex geological processes on each's sea floor. Of course, both of our neighbours have since lost such wondrous properties. As the smallest of the 3 planets, Mars cooled down from its primordial state much quicker than its siblings, and thus may have been the first world to become blue. However, because Mars is so small, its core also cooled down very quickly. Its insides went cold, thus causing the convection currents within its mantle to subside. This caused the planet's protective magnetic field to switch off, allowing harmful solar emissions to strip back the Martian atmosphere, and today all of its oceans have evaporated. Mars would have only had habitable conditions for a few 100 million years at most, probably not enough time for anything more than simple cellular life, such as bacteria, to emerge, but even then there's no guarantees. Venus, on the other hand, managed to retain its habitable conditions for longer. It is much larger than Mars, and thus its interior remains active, even to this day. Early in the Sun's life, when it was less bright and hot, Venus sat in a position analogous to where Earth lies today, just the right distance for temperate conditions which supported liquid water for more than 2 billion years. Multicellular life on Earth is thought to have taken around 3 billion years to evolve, but it's still interesting to think what could have occurred on Venus during its habitable epoch. Unfortunately for Venus, the Sun continued to evolve, gradually burning ever hotter and brighter, which gradually raised the planet's temperatures, causing its oceans to evaporate. This led to a build-up of water vapour in its atmosphere, followed by a runaway greenhouse effect of atmospheric thickening, which caused the planet's water to boil away completely. Now the planet is hostile, and experiences the hottest temperatures of any world in the solar system, thanks to its thick, toxic atmosphere and its close proximity to the Sun. Our 2 planetary neighbours were once Earth-like, but neither boasts anything close to the complex array of idealistic properties that make Earth so special. Today, Earth's natural balance is maintained by the life processes it has given rise to, and it has remained an optimal distance from the Sun to keep its climate temperate for billions of years, much longer than either of our neighbours. Earth is a standout world and a success story, a thriving oasis among scores of dried up deserts. But no matter how well suited we are, our barren companions are a constant reminder that balance simply cannot last forever. Though the Sun remains peaceful today, a new age is coming for the solar system. An age of change, destruction and evolution. An age for new worlds and new stories, but one in which the Earth has no place.